Hello, my name is Javier Rodriguez, and today I'll be doing a post-quiz tutorial for Physics 2212, Physics 2. The problem we'll be doing today is problem 16P43 in the book. And for this problem, we're given a thin hollow cylinder that's open on both ends. And with the left end is at the origin of our axis, and the other end is at a distance L from the origin, which is the length of the cylinder. And so the cylinder is oriented on the x-axis, and we are giving the radius of the cylinder is r, and we want to find the electric field at a location W away from the cylinder, right? So for this, we're also told that the net charge is the positive Q. In other words, the cylinder is positively charged all around. So in order to begin assessing this problem, the first thing we should do is find the direction of our electric field that we want to get at the end. So since we know that this is positively charged all throughout, that's a net charge, we know that the electric field points away from positive charges, right? So that means that our E field at a point here or anywhere is actually going to point in this direction. That means that our E field is going to be on the x-axis. What we get from this is that the y-axis and the z-axis of our E field were actually going to be equal to 0. That means that at the end we should get a vector that only has one component. The other two components will be 0. So now that we know that, we can begin actually trying to find the numerical value of the electric field. So we know that for an object with a distributed electric field, the best way to find electric field is to divide it up into little parts. We would find the electric field on all these parts, dividing the charge of the cylinder equally. So we find the electric field of all these directions, and then integrate over the length of the cylinder to find the total electric field. So we're gonna call the electric field of the small piece our DE, right? So for our DE, we know using the E-ring equation given to us in the formula sheet of the class, we know that we're going to need Z and Q, where Z is actually R. So we're gonna have to find a distance vector from W to our small piece. So first, before we actually try to find DE, we're going to try to find R. So R, remember, is final minus initial location, where our final location is our W, and our initial location is an object that is X length away from this part of the cylinder. So that means that if we want to find it, it's final minus initial. That means that, first of all, we can start by saying that the Z and Y components are going to be 0. We got this from finding our electric field beforehand. Now we know that this is going to be final minus initial from this equation right here. So that means that our final location is W minus X, which is the distance that part of the cylinder is from this part of the cylinder, from the right side of the cylinder. So now that we have that, we can proceed to find the distance, the R mag, which is actually equal to the square root of all components squared, which in this case is just this. So it'll just be the absolute value of W minus X. And then our R hat, which is the direction of this, only to confirm, is going to be 1, 0, 0, because these two things are the same, and this is equal to our R divided by our R mag. So we can confirm that the direction is actually in the X direction. After that, we have to find the actual charge we have to find Q, which is the actual charge of that small piece of the cylinder. So we're going to call that dQ, right? So dQ is going to be equal to our total Q times our dx, which is actually the thickness of that part of the cylinder. So it's going to be equal to our dx, and then you have to divide that by L, which is the total length of the cylinder, because we want to find only the charge of that specific point of the cylinder, only that specific part of the cylinder. So now that we have our dq and we have our r mag, we can actually find our dE, the electric field of that specific portion of the cylinder. So using the equation given to us from the equation sheet, our E ring, we're going to see that, so we have our constant, 1/4 pi epsilon naught, and then we're going to multiply that times our Q, which is actually this right here, so it's Q times dx over L, all that times our Z, which is W minus X. And then we got to divide that by our R3, which we know will be the radius of our cylinder. Right? So there we go. And now we know that this is actually a vector. And since we know the direction of it, which is only in the x direction, we know that it's going to be equal to this, and 0, and 0. So there we have the electric field of a small portion of our cylinder. So now we need to use integration in order to find the total electric field of the entire cylinder on the point W. So we know that for this integration, it's going to be bounded, over the length of the cylinder. That means it's going to start at this point right here and end at this point right here. So since the cylinder begins at the origin, we know they're going to be integrated from 0 to L, which is the length of the cylinder. And what we're going to be integrating over is actually going to be our electric field. So we know that because we're trying to find the electric field at all the points. So we know that this is what we have to calculate in order to find the total E field. It's going to be equal to 1/4 pi epsilon naught over Q dx over L times W minus X, all that over R cubed. Right? So this is what we have to use to find the electric field at all the points, the total electric field of the cylinder. So by using the laws of integration, we will actually see that our total electric field at the point W is actually going to be equal to a vector, which once again we know has a 0, y and z component, and it's going to be equal to 1/4 pi epsilon naught. Since we know this is constant and we don't actually integrate over it, all that times our Q divided by the length over R cubed, which is our radius, times W times L, all that minus L squared over 2. And this is going to be alright, and that'll be the electric field for our entire cylinder. Thank you very much for attending this, and I hope you learned something.